Hi everyone. Today we're going to cover dynamics. Dynamics is the study of forces and their effects on motion. First, we'll start by talking about Newton's laws of motion. His first law of motion is called inertia. Basically, things in motion will stay in motion unless acted on by external force, and things that are not in motion will stay not in motion unless acted on by an external force. His second law is that the force is equal to the mass times the acceleration. You'll use this equation to calculate the acceleration on objects and the net forces that are on the object. His third law is that every action has an equal and opposite reaction. This might seem a little confusing at first, but once we cover the normal force and go over free body diagrams, it'll make more sense. Basically, if you were to push on a wall, the wall would push back on you with equal magnitude and opposite direction of the force. The first force we'll cover is the force of gravity, which pulls objects of mass together. On Earth's surface, we can just use the formula that the force of gravity is equal to mg. This little g is the acceleration due to gravity, equal to 9.81 meters per second squared. But if you're not on Earth's surface, you might need to use the other formula down at the bottom. This is the gravity constant, the big G, times the first mass times the second mass divided by the radius squared, or the distance between them squared. For most problems in this unit, we'll probably be using the formula for the gravity on Earth, but in future units we'll have to use this other formula because we'll be calculating the forces of gravity on different planets. The next force is the applied force, and this is exactly as it sounds like. It's when you apply a force to an object. For instance, it can be when you push on a box. If the object is isolated, it'll follow Newton's laws of motion, where the applied force will just equal the mass times acceleration. However, if the object is not isolated, you will have to account for other forces in the F equals ma equation. The normal force is a force that will prevent objects from moving further. For instance, think of the scenario of a box resting on the Earth's surface. Gravity is pulling down the box, so why doesn't the box just keep accelerating downwards? Because the surface is applying a force to counter the force of gravity, which will prevent the box from falling further. This means that the net forces on this box will be equal to zero because the normal force is opposite and in the same magnitude as the force of gravity. The force of friction has two main components. There's static friction and kinetic friction. Static friction is the force that will prevent objects from moving when they're resting on a surface. For example, if you were to push on a stationary box, you would need to apply more force than the force of static friction for the box to start moving. The force of kinetic friction works to slow objects down once they're already in motion. In most scenarios, the formula for the force of friction is the coefficient of friction multiplied by the normal force. The coefficient of friction that you use will be for the static friction if the object is not moving and stationary, or if the object is moving, you'll use the coefficient of kinetic friction instead. The force of tension comes from ropes and wires pulling on objects. Think of a box suspended in the air by a rope, and then someone pulling down on the rope. The box will move up when someone pulls on the rope because the force of tension will transfer the forces to pull the box upwards in this scenario. The force of tension, the equation for it will vary depending on the scenario, but generally it'll be gravity plus whatever acceleration or external forces are on the box. Now lastly, springs also have a force. Think what were to happen if you were to compress the spring. It would exert a force trying to expand to its natural state. And then think of what would happen if you stretched a spring. It would exert a force, once again, trying to shrink down to its natural state. And this is the force of springs. It's given by what we call Hooke's law, which is the spring constant, k, times the displacement, which is x, or the displacement from its equilibrium position. So now let's talk about free body diagrams. This is extremely important to determine equations for when there's multiple forces acting on an object. The forces that we have talked about, aside from gravity and the spring forces, do not necessarily have one equation that fits every scenario. You'll have to determine what the equation will be that's appropriate for each scenario when you read the question. And this is what a free body diagram can help with. Basically, a free body diagram just shows all the forces that are acting on the object. If an object is accelerating in a direction, that means that there's an unopposed force acting in that direction. We will see this in the upcoming example. A 5 kilogram block is resting on a horizontal frictionless surface. A horizontal force of 20 newtons is applied to the block. Draw a free body diagram for the block and calculate its acceleration. Let's start by writing down the variables that we know. Mass is 5 kilograms, and there is an applied force of 20 newtons. Drawing the free body diagram, we see that there is an unopposed force in the horizontal direction, meaning that it will be accelerating in the horizontal direction. Additionally, though, we still need to calculate the force of gravity to complete this free body diagram. Calculating the force of gravity, assuming that this is on Earth, we see that is equal to 49.05 newtons. So now we can complete the free body diagram by labeling the force of gravity and the normal force. Now, to calculate the acceleration, let's rearrange the equation of F equals ma to solve for acceleration. We get that acceleration is equal to the force divided by mass, or in this case 20 newtons divided by 5 kilograms. And this works out to be an acceleration of 4 meters a second squared.